So welcome everyone to a new talk of the series of the Commission G5 of the IAU. And today it is our pleasure to introduce Katherine de Kleer. She graduated in physics and mathematics at the MIT, then did a master's in astrophysics and her PhD at the University of California in Berkeley. And she was an NSF graduate research fellow, was also a postdoc at Caltech with the Haney-Simmons Foundation, a 51B postdoctoral fellow, and she has a Hofstadter's family scholar from Caltech, and is currently an assistant professor of planetary science and astronomy at Caltech. Her talk today is entitled The Atmospheres of Solar System Moons at UV through Radio Wavelengths. So we are going a little bit even beyond the normal scope of our seminars of planetary atmospheres and atmospheres of stars to going even to atmospheres of moons. Welcome, Katherine, and the floor is yours. Oh, please keep your cameras off and microphones off, please. Thank you.
All right, let me share here. Okay. Well, thank you very much for having me come speak on this topic, which I know is a little bit out of field for this seminar series, or I guess field adjacent. So given the kind of breadth of the audience here in stellar and planetary atmospheres, I decided to give a fairly broad talk rather than focusing on some individual object. To kind of give a broad overview of the observational techniques that we use to study the atmospheres of moons specifically, including UV, infrared, and radio, using kind of a few important case studies to kind of talk about the science that is important that we can address using these techniques. So hopefully you learn some interesting new science and also potentially make some connections between the observational methods that we use in solar system and methods in exoplanets or stars. So our solar system gives us essentially four major planet and moon systems in the outer solar system from which to understand moons, how they form, how they evolve, and the processes that are at work on them. So you can tell, just by looking at these images, the great diversity of moons in the solar system. You see the range of different textures and colors that tell you about the geological processes that are happening on their surfaces, the radiation bombardment and what composition of ions and are coming in that way, and as well about the presence of the atmosphere. So the only moon here where you can really clearly see an atmosphere is Saturn's large moon Titan. So the other thing I want you to take away from this image is that, in this talk, I'm going to touch on a few key case studies, but in fact, it's not, I'm not going to touch on a subset of the large moons. I'm in fact going to give you an example from all of them. So there aren't actually that many large moons that have substantial atmospheres that we can study that really have these dynamic, are big enough to have this combination of processes from geological to atmospheric. So the large moons are the four Galilean satellites of Jupiter, Io, Europa, Ganymede, and Callisto. And the inner three of these are in the Laplace orbital resonance. And so we have tidal heating in particular in Io and Europa that have an impact on their surface properties and on their generation of atmospheres. In the Neptune system, Neptune's single large moon Triton is probably a captured Kuiper Belt object, and it has an atmosphere in part sourced by nitrogen geysers. And then Titan, the moon of Saturn, is the only moon in our solar system that has a really substantial atmosphere. It's denser than Earth's atmosphere. So we'll be talking about these moons and then also this little one Enceladus because of its plume activity. The broad goal in studying these collections of solar system objects is to put together a more comprehensive framework for, comparative planetology. Basically, how does each of these moons evolve to be exactly the way it is and not like any of the others? And from that perspective, each of these objects is basically a single puzzle piece towards putting that picture together more coherently. Okay, so how are the atmospheres of solar system moons in particular maintained? Not the sort of ultimate origin, but what is producing them in real time? Gas atmospheres, and I should say I will use atmosphere even when in fact it is an object that is just an exosphere in the sense that it is non-collisional. So I may use those terms interchangeably, but most of these objects, with the exception of Titan, have very tenuous atmospheres, and in some cases, they are exospheres. So what is producing these in real time that allows them to be there whenever we go and observe? There's three main processes at work. The first is sputtering of surface materials. So this is a process whereby if you have a high energy particle, let's say a high energy ion impacting the surface of these objects, there's a chemical reaction and it releases a species that may go into the atmosphere, and it may only be there temporarily, but because this is always happening continuously, you can sustain an exosphere in this way. In addition to that, if you have a surface that's warm enough and you have the right ices on the surface, you can have a sublimation of surface ices and produce a sublimation supported atmosphere. This is definitely seen for the case of Io and has been argued for water sublimation atmospheres in the cases of Ganymede and Callisto. And then the final process is this outgassing or plume activity. So the objects in particular that are geologically active, typically because they're tidally heated, may be outgassing from the interior or may even have these dramatic water geysers are on Enceladus or volcanic plume activity as on Io. So the atmospheres of the moons are produced by some combination of these three processes. And then once you have these gases that are going into the atmosphere of the objects, in particular in the cases of the outgassing and plume activity, that material gets lost from the atmosphere. These moons are not able, for the most part, they don't have enough gravity to hold on to substantial atmospheres over time. They can have relatively high mass loss rates, especially in the case of Io. And that material that gets lost goes out to populate the planetary system in which they're orbiting. So the south polar plumes of Enceladus source the Enceladus E-ring and also coat the surfaces of the other moons, from which point that material can be sputtered and support their atmospheres. In the case of Io, because Io is embedded within Jupiter's very strong magnetic field, the material that gets lost, much of it becomes ionized. And so then you have electrons and high energy ions that are going on to impact the other moons and in fact, producing their atmospheres in that way. Okay, so in order to understand this kind of collection of processes related to atmospheres, going from the geologically produced atmospheres all the way up to these atmosphere-magnetosphere interactions, we really need a multi-wavelength approach. And that is because each of the kind of wavelengths of study gives us different information on the atmospheres and gives us different perspective on the processes that are involved. So I've split this talk into three kind of small topics where I'm moving, I guess, longer in wavelengths. So I'll start by talking about UV and optical observations of aurora, specifically at Europa and Ganymede. The aurora tell you about atmosphere-magnetosphere interactions in the very upper part of the atmosphere. Then when you get to longer wavelengths, you can sense molecules directly. So JWST in the infrared is giving us a wealth of detections of molecules in the atmospheres of moons. And then finally, as you go to the radio, you can do things like winds, saying something about dynamics, and looking at molecular chemistry in more detail. All right, so starting off here talking about aurora and atmosphere magnetosphere interactions. So here I'm going to focus on talking about Europa and Ganymede. So let me introduce you just a little bit more to these moons, which I showed already on the previous slide. So the Galilean satellites go like on the left here is closest to Jupiter, moving outwards. So you have the most heating in the interior one, Io. So Io is a very unique object in that it is volcanically active, driven by this tidal heating. The other three of the moons in this system are what we call icy ocean worlds, meaning that they have a full ice shell surrounding a global subsurface ocean. Europa is the one of the places in the solar system, or Europa's ocean is one of the environments in the solar system that people consider most potentially habitable, and is the target of 2 missions currently on their way. And then Ganymede is quite an interesting case. It is the only moon in the solar system that generates its own magnetic field. And so as you can imagine from the perspective of aurora, it gives us a really unique piece of information. So if you know anything about the aurora of the Galilean moons, it's probably because you saw this result from 2014. So the aurora, I guess, were made most famous within the field by this group that kind of tentatively detected water plumes at Europa. So this was done in the UV using the Hubble Space Telescope. And what you're looking at here are images on 3 different nights in atomic hydrogen. And then when you subtract most of the reflected light from the disk, they show that there's this little excess off the edge of the disk. And this is the 1 sigma contour, which is why I say it's tentative evidence, it's low signal to noise, but is supported by the fact that there was a excess of oxygen there as well. And so this was evidence for water coming out of Europa. Of course, from the perspective of spacecraft mission, that's very interesting because it gives you the potential to go and directly sample. All right, so how are these aurora produced? I mentioned already that Io is sourcing this torus of plasma and neutral particles. The electrons that are ultimately coming from Io's volcanic gases after they become ionized are impacting the atmospheres of the other moons. And essentially, you have an electron that comes in, it impacts either an atom or a molecule in the atmosphere, but let's say it impacts a molecule, there's enough energy to dissociate that molecule into its constituent atoms, and those atoms are left in a characteristic set of excited states. So when they relax, they emit these auroral photons, and by looking at the ratios of the photons at different wavelengths, you can tell what the original molecule was that was dissociated. Okay, so my student, Zach Milby, put together a really nice little animated spectrum here to show you this. So this is basically a synthetic spectrum of the different auroral lines that we detect in the UV. So this is what I was just showing you before, as well as the optical wavelengths. So if the atmosphere were atomic oxygen, this is what the spectrum would look like. Then if you postulate instead that there's molecular oxygen instead of atomic, your line ratios change substantially. Now this red line becomes by far the most prominent. And then if you go look for a water atmosphere, here's how that spectrum changes. So what you probably notice here is that when I went from molecular oxygen to water, the main change is that green line becomes really strong. And so the best diagnostic for looking for water, whether that's a sublimation atmosphere or plume activity, is by looking at this green line at visible wavelengths, and in particular by taking its ratio to another line. So we look at the green to red ratio, and these are the same emission lines that you see in the aurora and Earth's atmosphere as well. And looking at their ratio gives us a really strong diagnostic of molecular oxygen versus H2O, which are two of the strongest candidates for molecular constituents in the atmospheres of these objects. Now, the problem with observing in the optical is that these moons have very bright reflective surfaces, and the sunlight reflected off their surfaces completely swamps the signal that you would see from these auroral emissions. So what we have to do is observe them during this short window when the moons are in eclipse by Jupiter. So this is a kind of stitching together some raw data from observing that at Keck just to show what that looks like. So in this case, it's Io. So when it's in shadow, those little dots that you see are thermal emission from the volcanoes. So you see Io come out from behind Jupiter. When it's in the dark there, when it's in Jupiter's shadow, it ends up being like 1 to 2 hours where we can actually detect those atmospheric signatures. Then once it comes out into sunlight, those signatures are completely lost in the noise. Okay, so since this may be a group of spectroscopists, or at least some of you, I thought I would for a minute just show some actual raw data just because it's so cool. So on the left is what the data look like for our optical observations of these aurora. So this is data from the high-res instrument, which is a high-resolution spectrograph on the Keck telescope. And if you zoom in, this is wavelength axis, this is spatial along the slit. You can see the emission from Europa, the auroral emission here in one of these emission lines. And then you can see the same line at Earth. And the Earth line you see fills the spatial axis because, yeah, it's everywhere. And then Europa is localized to this particular location. And also you'll see that it's shifted because of the relative motion of Europa and Earth. So that Doppler shift is also what allows us to make these observations. Okay, so we have been in recent years expanding the observations of aurora of Galilean moons into the visible part of the spectrum. I'm not going to go through everything here, but this is a plot that shows a bunch of the different detections that we made. Many of these lines were detected for the first time at these objects, or in fact, anywhere in the solar system, or sort of are among the first places in the solar system that these lines were detected. I won't go through this whole list. I'll just show you a couple of key examples. So for example, there are a couple of oxygen triplets that we've been observing that we detected newly at Ganymede and one of them at Europa. And this is what those observations look like. So on the top, you see the spectra, and even where the spectra are pretty low signal to noise, this is the detector image that I'm showing because you can see that the emissions are in fact localized along the slit to the location of the moon, which is lens robustness, even in the case where the spectrum itself looks pretty low signal to noise. So this is Ganymede and Europa. They're kind of far enough in that they have a reasonably high, local electron density to actually excite these aurora. When you go out to Callisto, you're now getting far enough from Jupiter that the electron density is thought to be pretty small. Aurora had been seen at Jupiter or at Callisto before, but it was unclear because they were observed in sunlight whether that was being excited by photons or electrons. But we newly detected aurora at Callisto when it was in shadow, so kind of directly telling you that in fact these aurora are being excited by the electrons. So that was exciting. Callisto, we want to follow up on this to actually, put constraints on the composition of the atmosphere, but Callisto only eclipses every 6 years-ish. So we haven't been able to return to this campaign, but next year it will start eclipsing again. And hopefully we can actually detect more than just this single red line. Okay, so using these lines to say something about composition, we look at the ratio, and in this case, I'm showing the ratio of the red to green line as a function of time over the course of a single event. So if this ratio fell on this dashed line here, that would be diagnostic of molecular oxygen composition, whereas a ratio down here would be atomic oxygen or H2O. And so you can see that our data points are most consistent with the molecular oxygen atmosphere here. But because your average is in fact below this line, there's some evidence for a constituent that is not just molecular oxygen. We can't differentiate between these two scenarios based on this ratio alone. But the reason I didn't just plot this as a single point and actually showed it to you as a function of time is that if the atmosphere were the case, or there was a strong component anyway of molecular water, then that would be produced by a surface that was sublimating. So when the surface is in sunlight, it's warm, it sublimates water. But then you would expect that when it goes into shadow, you would see a kind of drop in the presence of this water atmosphere. So you'd expect a ratio that maybe starts down here when the object first enters shadow. And then as the surface cools and the atmosphere freezes out, the ratio would follow maybe a curve like this. And we don't see anything like that. We are actually going back and revisiting these observations with that specific goal in mind. But so far, we don't see evidence, really strong evidence for water, at least in substantial amounts. Okay, so we think that the atmospheres of these satellites are predominantly molecular oxygen. This is a good reminder that molecular oxygen alone is not a biosignature, because it dominates the atmospheres of these objects whose surface environments are very much not habitable. In addition to composition, I'll briefly mention the aurora also can tell us about the local plasma. And the reason that this works is because the orbital plane of the Galilean moons is tipped relative to the magnetic equator of Jupiter. And so the moons, as they go around Jupiter, are actually moving kind of in and out of the regions of densest plasma. So if we think we have a good model for local electron density, you then can plot the brightness of the aurora as a function of electron density. And there's one very cool demonstration of this from the spatially resolved data that we got from Keck. Poor spatial resolution, but still spatially resolved. So Ganymede, as I mentioned, has its own intrinsic magnetic field. And so in contrast to the other moons, its aurora should roughly follow these same auroral ovals that we have on Earth. They have a slightly different geometry because Ganymede is embedded within Jupiter's, so deeply within Jupiter's magnetic field. But the aurora, yeah, should be localized to these two auroral ovals. So this series of snapshots shows an image of the oxygen aurora at Ganymede as it's moving from above the region of densest plasma through and then to below the region of densest plasma. And what you can see in these series of images is at the beginning, when it's above the densest plasma, the southern auroral oval is mainly lit up. And then you can see it actually transition through into the northern auroral being lit up. So whichever auroral oval is kind of facing that region of densest plasma is the one that's primarily illuminated. And you can also kind of look overall at the brightness of the aurora as a function of vertical distance within that plasma environment. And these curves show the model that you would expect. And you can see that the data points kind of follow that, but there is a substantial amount of stochastic variability. So the aurora are kind of driven in part just by, where you are relative to this plasma equator. But there's also substantial variability, which could be variability in the atmosphere or could be variability in the plasma. So by surveying this whole range of different auroral wavelengths, we're able to say something about the composition of the moons, how that composition might be changing as a function of time of day, and even about the environment that they orbit in. Okay, so I've been talking about using atomic emission lines to try to say something about the molecular composition of the atmospheres. But if we go to the infrared, and for certain molecules, we can directly detect molecular bands, in most cases, rho vibrational or rho vibronic bands in the near infrared with JWST. So I want to transition now to talking about that a little bit. And this section is, less of maybe a single narrative arc and more of a kind of overview of the exciting things that JWST has revealed to us in the past year, basically 1 to 2 years, on the molecular atmospheres of moons across the solar system. Okay, so we've been talking a bit about Callisto already. When you point JWST at Callisto, this is what its spectrum looks like. And what essentially everything that you're looking at here is a reflectance spectrum of its surface. So these features are just absorption features in the ices and solid materials. This very strong band here is the CO2. But within this CO2 band, you might be able to see on your screen that there's a little bit of a ripple here. And if you actually take the continuum, which again is just the solid state feature, and subtract that off, you see that ripple in the residual spectrum. The spectrum here is in black, and a synthetic CO2 gas spectrum is in orange there. And you can see that it's a remarkably good match. So these ripples are not just, artifacts in the spectrum, but in fact, very diagnostic of the presence of CO2 gas. So CO2 had been detected once on Callisto before by spacecraft, but just in one specific location off the edge of the disk where they were able to make that detection. With JWST, we can now actually map it across the surface. So you get a spectrum, maybe relatively low signal to noise, but you get a spectrum for each pixel across the disk. Now, if the CO2 were being produced by, let's say, sublimation of some CO2 ice that was in the subsurface, then you would expect its distribution across the surface to basically follow surface temperature. These two panels here are maps of surface temperature for the two hemispheres. And I should say for all of these moons, they are tidally locked to their host planet. And so they have the anti-Jovian and sub-Jovian hemisphere, or anti-Saturnian and sub-Saturnian. And they also all have a leading and trailing hemisphere in their orbits. That's just what it sounds like the front and back hemisphere. And this can be, frequently moons are observed in both hemispheres because there are different processes acting on them. For example, the plasma in the Jupiter system is impacting the trailing hemisphere primarily. And so frequently these will be shown in both leading and trailing because there are potentially different processes at work. Okay, so you can take these maps of surface temperature and compare them to the CO2 gas distribution, and you see that the gas distribution, again, it's noisy, but where it peaks does not line up with the regions of highest surface temperature. And so it's unclear what exactly is causing this specific distribution of the CO2 gas. Oh, sorry, I've lost my mouse here. Okay, there we go. The specific distribution of the CO2 gas, but the fact that it doesn't just align with surface temperature is telling you that there's some process that is not just thermal. So it could be radiolytic, it could be geology, it could be that there's actually, somehow an underlying different distribution in the carbon source species that is leading to the production of CO2. By the same approach, we've also been able to see CO2 on Ganymede. So this is basically that same low vibrational spectrum that I was showing you for Callisto, but now for Ganymede. And this is the distribution on Ganymede for the leading and trailing hemisphere. So broadly speaking, you see that the CO2 is present over much of the trailing hemisphere, but not the leading. But the thing that is most striking about these distributions is that the primary place that you see CO2 on Ganymede is in the north polar cap. So Ganymede has these green lines here are the open closed field line boundaries. And you do see, just based on the brightness of the surface, north of this region, there's a Ganymede's polar cap. And the hypothesis for why you would have so much CO2 in the northern hemisphere is, or at least one hypothesis from this paper, is that you're warming the more equatorial parts of the disk, and so whatever CO2 you're sublimating there will preferentially freeze out in the cooler regions. So it'll be cold trapped at the poles, and once it's there, it's cold enough that it won't sublimate as efficiently from those regions, and so it kind of builds up there over time. And then, so that kind of leads to a higher density of CO2 ice in the polar region that is then subsequently released by sublimation or sputtering to see the gas species that you can pick up with JWST. All right, moving briefly to the Saturn system now from Jupiter. The Cassini spacecraft made extensive observations of the water plume on Enceladus that you see here in this image. But what you're looking at here is really, within one Enceladus diameter away. What James Webb was able to do is map the density of this plume to really quite extensive distances from Enceladus. So if you can't read the axes here, this is an image of the Enceladus system in water emission. And from here to here is 100 Enceladus radii, so much, much bigger in scale here. And you can see water emission, and now this is fluorescence emission. Most of the spectra I'm showing you here are the rho vibrational, but this one is fluorescence. And you can map the water out to tens of Enceladus radii away and get the density. You can get the rotational temperature, which is important, for example, for modeling observations at other wavelengths. And you can get the plume outgassing rate. And actually, what they were able to derive from this plume measurement here, the outgassing rate that they derived pretty well matched the outgassing rates that were measured by just looking close to the plume itself from the Cassini spacecraft. So also within the Saturn system is Titan, and Titan's atmosphere really deserves a whole talk in its own right because there's so much going on there. But these are some images. So as a reminder, Titan is the one kind of dense atmosphere on a solar system moon. These are images on the left. It's in the 2.1 micron filter. These are from NearCam on JWST. And on the right, it's 3 different filters together, 1.4 to 2.1 microns, I think it spans. And so essentially, Titan's atmosphere is mainly methane. So by looking in and out of the methane bands, you can play these games where you can look at different altitudes within the atmosphere, upper atmosphere, middle atmosphere, and then all the way down to the surface. So in this image on the right, you're seeing these dark regions are actually surface features. And then these brighter regions are clouds that you can then track and compare to spectral observations. So Titan's spectrum with JWST is just phenomenal. We get incredible amount of detail and it can detect numerous molecules. Much of this spectrum had been previously observed with Cassini, but we've gotten a couple of new things from James Webb. The methyl radical, CH3, has been detected for the first time now. The high sensitivity of James Webb has allowed us to look in great detail at these specific bands for the molecules of CO and CO2, for example, and has shown us that in these cases, these molecules are not in local thermodynamic equilibrium. So this has motivated more modeling to more deeply understand the atmosphere of Titan and what the thermal equilibrium state is. So the same is the case for Io. I think this is my last James Webb example. This is a James Webb observation now of sulfur monoxide emission from Io. And it's a rho vibronic transition. And so you see all the different branches. This is just the model for LTE case at 200 Kelvin. And it had been observed before, but not in great detail, that there was an excess of emission around 1.69 microns. But the sensitivity and lack of Earth's atmosphere contamination from James Webb has allowed us to really resolve that in great detail and has confirmed absolutely that this gas is out of local thermodynamic equilibrium. The red here is a model, but it's a model that's just artificially increasing the population of the states with the high rotational quantum numbers. So again, this is now motivating models that are self-consistent models that are actually kind of physically looking at the non-LTE state of Io's atmosphere. So just to briefly summarize what we've gotten from James Webb, we've detected numerous new molecules, and in many cases, for these rho vibrational bands, have been able to say that these objects are not in LTE and has motivated a deeper look into what's going on in these atmospheres. All right, so the final topic I want to touch on here is now using radio wavelengths. So we're still talking about molecules, but now at radio wavelengths to understand sulfur on Jupiter's moon Io. So from an atmosphere's perspective and from a number of molecules we can detect in one atmosphere, really Titan and Io are two cases where we can detect kind of a wide swath of chemistry. So Io's primary volatile is sulfur. It doesn't seem to have H2O. It doesn't seem to have CO2. And that sulfur is being outgassed by the volcanoes. And then, as I've mentioned a few times, it's being kind of impacted, ionized, and lost by these interactions with charged particles and energetic particles in the Jupiter system. And that the loss, so the material is being lost at a rate of somewhere between 1,000 to 3,000 kilograms per second, and what remains may freeze out onto the surface and get reincorporated into the interior. So Io hosts this interesting sulfur cycle where there's recycling between the surface and interior, as well as this loss rate. So using ALMA, we can look into Io's sulfur dynamics and Io's sulfur chemistry. These are, a variety of different observations of Io with ALMA. These are kind of compilation of some past observations. And these ones here are all SO2, everything except for the two in the lower right. And so broadly, the SO2 atmosphere is just kind of evenly distributed between northern and southern mid-latitudes. The reason that it looks bright towards the edges of the disk are just because of a geometric effect. They're optically thin. And so you just get a longer path length for emission there. Occasionally, you see these blobs that are probably enhancements due to volcanic plumes. And then when you go to the NaCl panels, all of the emission is in little blobs there because those species exist exclusively in volcanic plumes. So ALMA gives us the high spectral resolution to actually measure Doppler shifts and derive wind fields. This is a kind of schematic showing the proposed components to Io's wind field. The dominant component has been proposed to be a sublimation-driven flow where near the subsolar point, you are producing more atmosphere by sublimation. And so there should be a day to night side flow. There may also be an equator to poleward flow. And then near the volcanic plumes, you also have a flow away from the volcanic centers. So by making maps of Doppler shifts, we were able to derive Io's wind fields. The top three panels are for Io's wind field on the leading hemisphere, SO2 on 2 dates, and then NaCl. And then the bottom is the trailing hemisphere wind field. And I think, there's a lot I could say about these, but the first order takeaway is that, the top panel looks all blue and the bottom panel looks all red, or the bottom row. So the leading hemisphere, the atmosphere looks primarily blue shifted coming towards you, and the trailing atmosphere looks primarily red shifted moving away from you. And this is not consistent with the sublimation picture alone. It's not consistent with the volcanic plume picture alone. And what we think is happening here is that these, so the trailing hemisphere moving away from you and the leading hemisphere moving towards you means that the atmosphere is always moving, broadly speaking, in the direction of motion of Io. And the only factor that can really produce an effect that's always in the direction of motion of Io is plasma effects. So the plasma in Jupiter's magnetosphere is overtaking Io, moving at moving at a higher velocity than Io. And so what we think is happening is that is imparting some momentum to the atmosphere and is actually driving Io's primary winds, even though those interactions are happening much farther out within the atmosphere than the altitudes where these observations are being made. Okay, so plasma-driven winds that are kind of maybe in addition to this sublimation-driven flow are a really primary component in driving Io's wind field. So we can also use these emission lines to do sulfur chemistry. So this is what the spectra look like that correspond to the images that I was showing you before. And the same lines that we've been using to do dynamics, we've also been using to do some geochemistry at IO. So we're specifically looking at sulfur isotopes. So this is looking at the ratio of sulfur 32 to sulfur 34. And the best fit model from a pretty simple radiative transfer model is shown here. The free parameters are the temperature of the gas, the column density, and then the mixing ratio of the sulfur 32 to 34. And you may notice that the models here are not a perfect match to the data. Part of that is actually happening because when we first did this analysis, we didn't incorporate this whole derived wind field. And so a lot of that mismatch is actually because of the winds. So we're redoing this analysis now, incorporating the wind field, and it gives a much better correspondence. So why do we care about the isotopes? What does that tell us about on IO? So I mentioned this sulfur cycle where you're losing material and recycling what's being left behind. The material that's being lost is preferentially the light isotope. By molecular diffusion, you preferentially are having the lighter isotope at high altitudes and the heavier isotope at lower altitudes. And so over time, your sulfur reservoir is getting progressively heavier, the kind of overall reservoir that's participating in this recycling and loss process. And so we measured the isotope ratio, kind of predicting that it would be heavy due to this long history of Io's volcanism and mass loss. And that is exactly what we observed. So Io's atmosphere plots heavier than anything in the solar system, except maybe H2S and Comet Hale-Bopp, although that has quite large error bars. But certainly compared to any of the rocky objects, Io sulfur is extremely heavy. This actually tells us quantitatively how much of the sulfur that's participating in this mixing and loss process has been lost over time. And if we convert this sulfur isotope ratio to an amount that has been lost, we actually find that Io has lost almost all of the sulfur that's participating in this process over its history. We argue that the sulfur that's participating in the process is all of the sulfur in the mantle and atmosphere, so excluding what's locked in the core, because Io is so strongly tidally heated that there's efficient mixing in the interior. So this seems like a big statement to say that it's lost almost all of its available sulfur, but actually if you take Io's current mass loss rate and you just multiply that out over the history of the solar system with the assumption that Io's been active over this entire time period, you basically get this same number. So our, best fit measurement finds Io losing mass a little bit higher than its current rate over the history of the solar system. So maybe some evidence that the mass loss rate has been higher in the past. So just by looking at these gas lines in the atmosphere, we were able to say that Io has in fact been volcanically active for most of this history. And because that volcanism is driven by tidal heating, that reflects on the longevity of the tidal heating and the orbital resonance between the three moons, and actually fits quite nicely with formation scenarios, which generally predict that these three moons get captured into orbital resonance essentially at the time of formation. Okay, so to summarize this kind of ALMA piece here and the sulfur on Io, ALMA gives us this wealth of rotational emission lines for SO2, SO, isotopologues, NaCl, this whole variety of molecules. From that, we're able to do atmospheric dynamics from Doppler shift wind studies, and also chemistry that can really inform our understanding of the formation and long-term evolution of this object. Okay, so we've talked about a whole variety of observations of solar system moons, from the aurora that tell you about the atmosphere magnetosphere interactions, all the way to this kind of sulfur chemistry that can tell you about the history of geological processes. And broadly, these are all contributing to our understanding. These multi-wavelength studies help us understand the atmosphere, from the source terms at the surface all the way up to the loss terms in the upper atmosphere. I'll close there and happy to take questions or have some discussion.
Thank you very much for a very nice talk. So we have time for, okay, John Plain, please.
Yeah, thank you. That was a very interesting talk. Regarding IO, I noticed on your slides sodium chloride showed up a few times, and I wondered if you could say something about that. Presumably it's also got a volcanic source, and I think one of the slides showed it's then photolized to make sodium atoms.
Yes. So I didn't have time to go into that story in as much detail, but I think it's on the slide as well. So the sodium chloride, and also we observe potassium chloride with ALMA as well. They are outgassed in the volcanic plumes, and that is predicted by these magma degassing models. But the lifetime of those in the atmosphere is very short, like at most a couple of hours. So whereas the SO2 that gets outgassed will stay in the bulk atmosphere in equilibrium with the surface, but the NaCl and KCl are really only present in volcanic plumes. So the one case where I showed, NaCl shows up in these blobs because it has to have an active source to be observed.
Mm-hmm.
It then does become ionized through a variety of different processes. And so you see sodium and chlorine in the greater Jovian magnetosphere. We actually looked at the chlorine isotopes with ALMA as well, and they're quite consistent with the sulfur ones, and that chlorine shows up as very heavy, but it's a bit harder to interpret that measurement because it's many of the important factors in the calculation are missing because people haven't studied gaseous NaCl as much in the lab as they have SO2. But also there's just so much stochasticity in this molecule because it's really only present in volcanic plumes. Yeah, so hopefully that answers.
Thank you. So, I mean, the sodium that is produced then is going to be quite localized. As you say, it's produced quickly from photolysis and then it's ionized also quite quickly. Or do you see a sodium cloud extending sort of quite far from IO?
Yes, absolutely. And this has been studied for a long time. And the reason so the sodium structure around IO is very complicated. There are different loss processes, and recombination then produces sodium atoms. And so you have the material that's ionized, spread throughout the Jupiter system, but then becomes atomic again through different pathways. And the large-scale sodium structure is observed easily out to hundreds of Jovian radii and can be monitored and shows quite a lot of variability. So there's been these multi-wavelength campaigns, monitoring the oxygen ions, the sodium ions, the sulfur ions and the sodium atoms, all in these really large scale structures.
Okay, thank you.
Dennis, please.
Yes, thank you for a very interesting and very rich content presentation. I have thinkings about the aurora and the question of detecting oxygen on exoplanets, and arguably searching for aurora could be one way of trying to find such a potential biomarker. So the question is, do you have some feelings? What would be the optimum conditions? You mentioned, for example, the issue having a bright surface will sort of blind it. So presumably one should be looking for some dark exoplanet with a strong magnetic field or something like that. Do you have any comments in this direction?
So you mean specifically looking for like the visible wavelength aurora or UV aurora like we're doing here, right?
Yes, I realize it's not exactly an easy task, but if one is to search for biomarkers, that would be something one could conceive of, and arguably it could be easier or less difficult to find an auroral signature than to look for some specific absorption line feature.
Yeah, so my intuition is that would be challenging, but I guess exoplanets give you so many different environments that maybe you will have an optimal one there. So I guess you need a situation where the auroral lines are not being completely swamped by reflected sunlight. But maybe you can play games with that with, the brightness or the albedo of your exoplanet. the temperature of your host star, and then maybe if you see something on like the night side of the exoplanet. But you need, I guess the things you would want to optimize are the amount of atmosphere that is able to be impacted by electrons. So maybe, maybe you'd want to not have a strong magnetic field on your exoplanet, or maybe if you have a magnetic field, it's fine because the aurora are still exciting kind of at that open closed field line boundary. But you certainly would want a densely populated magnetosphere for your star. That would be essential for producing the excitation. Yeah, it's kind of an interesting thought exercise.
Okay, thanks for the comments.
Carl?
Hi, that was great talk. Regarding the gases on Titan that you're seeing, you mentioned some of those are out of thermodynamic equilibrium, at least locally. And I wondered if you thought there might be any evidence for like plasma interactions that could put it out of equilibrium. It's a pretty dense environment, so it's surprising that it can get out of equilibrium. And just wondered if you had further thoughts on what does that.
Yeah, that is a good question. And in the case of Titan, I am not sure. That's one of the areas that is farther from my expertise. We've obviously thought about it a lot for IO and the SO, but yeah, I'm not sure what the source for the non-LTE is, but agree with you that the upper atmosphere is the place where that's most likely to occur.
Interesting. Thanks.
Hey, Carlos?
Thanks a lot for the talk. What I was intrigued by these plots that you showed discussing how the atomic forbidden lines of oxygen could reveal the different concentrations of oxygen, of atomic oxygen or water. What is the mechanism by which the excitation of these forbidden lines connect so tightly to these concentrations of these molecules?
Oh, so the question is, why is it that the set of excited states is so different if you're impacting water versus O2?
Right.
I'm not sure I have a detailed mechanistic answer to that. Maybe Carl.
I imagine the answer may be quite quite complex, right? I thought, to which extent it was understood, or it's kind of, I guess, more phenomenological. From the modeling, you find out that there is such a connection, right?
Yeah, I'm sorry, I'm just not sure. That's beyond my knowledge of the mechanisms. But if Carl or others actually have an answer, feel free to weigh in.
Carlos, you lost me a little bit in your question. Can you kind of restate it?
Well, the connection, the excitation of the two forbidden lines, the 5577 or the 6300, the ratio is connected very much to reveals the concentrations of the relative concentration for O2 and H2O, right? So I was wondering why there is such a connection, right? How, why that will happen if that was understood.
Yeah, I think I'm alongside Katherine there, where we all know that it happens, and you can make the line ratios based on other people's papers. But my intuitive understanding of the atomic physics that comes out of smashing these molecules with electrons in terms of why it happens, I just do not know. And I'm not the only person that this question could be deferred to here. If anyone else has more to say about it than either of us, please chime in.
Okay, I guess you've stumped us all.
Yeah, good one.
Sorry about that.
Oh, no, it's important to point these things out when you really, yeah, thanks.
Okay, so we have still time for another question. Okay, if not, so Katherine, thank you very much for a really great talk. And
Thanks for having me.
Thank you so much.
Yeah, thank you.
And thanks everyone for connecting. We'll be in touch.
Thank you very much. Pleasure.
You.